These lessons from Math1c 15.7. We're going to learn about divergence theorems. Divergence theorems. What's the purpose of that? Just like green theorem we learned before, green theorems is to make finding work done along a curve, along a closed curve. So we have a closed, simple curve. Okay, closed, simple curve, much easier. Divergence theorems. Okay, divergence theorem is to make finding flux over a closed surface. Has to be closed because if the surface is open, it won't work. Okay, has to be a closed surface. Much easier. So let's say this is a flat. This actually come from green theorem. Okay, so how the divergence theorem come from is they actually get the idea from green theorems. So what Green did was that in his book, okay, in his book about the work done, he had this graph, and he had this one. He said there's a vector field function. Okay, this vector field function can be decomposed to two sides, two vectors. One vector is a tangent vector, one is a normal vector. And then this come down here, this part is just a f dot tangent, the length of that, okay? The length of this part, okay? The length of that is a f dot t. We did that in 12.4 also, okay? So we did the essential force can decompose, right? These times the vector force, okay, decompose the two sides. One is a f dot t, that's a tangent. One is a f dot n, that's a normal vector. And this is a uninormal vector we talked about that last time. So this one, Green only used this one. He said this is the work done along this curve, okay? Because every tangent point, you can use to calculate the work done along this curve, right? And then this is a Green theorem. So the Green just do this part, line integral, and then he didn't touch this one. So when someone get the whole for I think that his name is Gauss. So that's why this divergence theorem also called Gauss theorem. But there's a debate there. Some people said that someone else used it before, and some people said that he used it first. So we don't know. So that's why some book called Gauss theorem, some book just called divergence theorems. And then the Gauss theorem, divergence theorem, I should say, because in America we call divergence theorem a lot. Okay, I heard in Europe they use Gauss theorems. So divergence theorem is using the part that Green theorem didn't use. He left this one here on the book, but he never touched it. Okay, and then the people found that this can be calculated for the flux across the surface, right? So they first do the two-dimensional surface first, but two-dimensional surface is no help. Why is that? I mean, it's really meaningless. The reason is divergence is about connect volumes, okay? So therefore, they want a closed surface. So for that's why you don't hear about flux for two-dimensional, okay? You can calculate. You can say flux for two-dimensional, but really not much not a good idea to learn a flat a surface that flat for two-dimensional. Usually flux is usually for three-dimensional surface. Okay, this is a flat because Green theorem only do flat surface. Okay, so 2D. Okay, and then so when you do a 2D flux, it's useless. But then they get the idea. Okay, from a 2D flux, they were able to make it to be a 3-dimension. And so after the vector field, Green theorem connect the line integral with an area. Okay, this is a flat area. Okay, not a 3-dimensional area, not a 3-dimensional surface. Okay, this is a flat. Okay. But divergence theorems connect surface integral. Surface is already included flat and includes 3D also. Okay, so surface include everything, include the 2 dimensions, 3 dimensions. with the volume, that's the most important part. So when you talk about volume, that becomes a closed surface. That right? A flat surface, means an open surface cannot talk about volume because a hollow means you're not close to it. Okay, so just like you have a surface. Okay, even though it's a curved 3 dimension, but if you open this part, okay, liquid, everything just go inside and go outside like that. But when you close it, okay, when you close this part, and then they can only go outside, right? So what they did, they said that, so what divergence theorem tells you that, it said the lead source, the whatever in, okay, in, out, okay, if you're gonna the lead in, the lead, whatever lead inside, so you go in, you go out, so you have some, let's say something that get to come out, right? You take all the in, okay, subtract all the out, okay, and then that will equal to the volume integral of the divergence that stays inside. So maybe I do it like that way. So let me write out first, then I tell you. So what the divergence theorem? Divergence theorem only talk about volume, okay? They connect the surface integral to the volume. So because we are looking for, okay, for flux. So let's say I have a balloon, okay? I have a balloon. And then I want to see that what's the air flow across my balloon, okay? Let's say the surface integral. So I'm going to calculate the air across it, okay? Cross out. And then let's say it's very hard to calculate this because we know that, right? We know surface integral is very high. You parameterize this is surface, so it's very tough. So what they do, they said that you're gonna have an air go inside, okay? You go inside, so this is in. And then let's say because your balloon leak, usually they do, right? So it's not every, so they sometimes they leak very slowly, but they leak. And then some are you in and then you're out. You're out also, a little bit out. Okay, so this is out. So what they said, you take all the in air, okay, subtract all out air, and then that's your left flow. Okay, and then they say your left flow is equal to the volume integral, inside the solid multiply by divergence F, okay, the vector field. So that's exactly what this means. They said surface integral means for this is surface, okay. If I want to see how much air go over the balloon, all I need to do is calculate how much in, subtract how much out, okay, the left flow, okay. It basically calculates the volume inside, whatever left inside, times by the divergence. That's why divergence also means the source away from, okay, away from the source. You throw away from the source. So, and that's basically the idea of it. So that's why they said the first means the left flow, okay? The left flow is equal to the volume. Now this is the left flow is equal to the volume, this is the volume here, they use a Q, Q stands for volume, multiply the divergence. Now, what's the purpose about, some benefit of learning divergent integral, divergent theorems. And let's see. Now, has a closed surface, okay? So divergence have a closed surface. So some of the things we use a lot in divergence theorem, okay? So that's the purpose of it. And they use in electricity. Electricity flow, heat, air, and fluid, and on gas also, okay, this one. So the formal definition for divergence, okay, so this is a purpose, and then it's a divergence okay, divergence means the net rate change. So net rate change with net flow, okay, net rate change with respect to time. This is respect to time. Respect to time of mass of fluid. I just use a fluid, okay, you can, or heat or whatever, or fluid flow from a point per unit volume. Okay, this is a volume, sorry, the writing. So they means that if I have a little tiny here, okay, this is your dV, okay, little volume. They want to know that in and out is a whole, okay, let change. There's a in, there's a out, right? If a same amount in, same amount out, then you have low divergence. It's that the in, there's out, they may not be exactly the same amount, okay? They said let change, means that in subtract out, okay, that's a net change. So that's why the net rate change means that the net amount in and out with respect to time, so like a speed change of a mass flowing, whatever you flow into this tiny little place, okay, per unit volume means this is a unit volume. So it means that in this little tiny bit, what's the speed of changing for the amount, okay? How much in, how much out, and how fast they change. So that's basically it. So you basically see three. So this is purpose is for this kind of thing, okay? Divergence means this. This is a formal definition. And this, what I do here, I just erase those, just kind of like explain the formal definition. And then here's the three types of situation you are seeing, okay? For divergence. Three types of situations. First of all, if your lead is coming out, okay, if you let air coming out or let gas coming out, okay, if the lead is coming out, then your divergence will be greater than 0. Okay, just like boiling water. When the water boils, the air comes out, right? So the lead is comes out, okay? There's air going inside, but the lead is coming out. So divergence F greater than 0. And the second situation is if a lead is going inside, like blow a balloon, okay? if you blow a balloon inside, the air is going inside here, okay? And then in that case, your divergence will be less than 0. So when you're in, your divergence less than 0. And if you are in and out the same, so you come in, but they immediately have the same place to come out. There's no lag. So water flow in and flow out right away. In that case, your divergence is equal to 0. This is for 3 dimensions, okay? We're talking about. And then the last thing is, remember I said divergence actually comes from green theorem, okay? So I didn't give you guys a graph here. So maybe I'm not going to go through the green theorem again because you guys already know. I was thinking to compare them. So I didn't do a little bit for earlier, so that should do it. And then I just go through a how to calculate divergence theorem. So formula. I gave you a formula earlier, right? But I learned how to use the formula. So this learn how to use the formula. So we said surface integral n's normal vector ds is equal to, I love divergence theorem. So just like green theorem, it makes things a lot easier. So green theorem connect the area, divergence theorem connect the volume. Okay. So what it said, let's see if a hemisphere, okay, the bottoms are closed, so that's my surface. The bottoms are closed, okay? And then my normal vector is right here. It has a perpendicular level curve. Okay, this is a unit normal vector. I didn't tell you guys they normalize it, but they're able to reduce, right? So they're able to reduce the length. And so to calculate this one, your n, okay, to calculate n, again, you can have a 2 way to calculate. We know that one is you can use a gradient, okay? If g is given, that means if the surface function is given, okay, I will try this one first, gradient, okay? If it's not given, now, it doesn't mean if you try this, it will work. Because sometimes you cannot integrate. You know, you can use a gradient, but doesn't come out, depending on your vector field also. But this is a special case. It's just like when you solve the quadratic equations, the special cases that you can factor, right? If you couldn't factor, you use the quadratic formula to solve. So if this one doesn't work, then you can parameterize the surface. Then we can use U, okay, cross RV. This is parameterized surface. We can use UV plane, or you can use it. It could be X or Y, okay? They just use UV, but it can be theta and phi, or can be SYG, or can be X and Y, S and G, and G and theta, like cylindrical, spherical, those are parametric surface. Okay, and then so that's how you get the n. And so your n is 2 choice, right? And the d, after you get the n, then your ds should convert to the region. Okay, you look like this one's a closed region here. And then you change to R. So your S F dots N is same as ds is same as R F dots del G dA, and that's same as R F dots RU cross RV and dA. And that's what we did. Now, we know that how difficult it is because you have many faces to make one surface. where you want a closed surface, then you're going to take forever. We're going to do a problem like that. You can see the benefit of this one. So what divergence theorem tells you that instead of you calculate instead of calculate the line integral along this surface, you can just calculate the volume, how much inside this volume here, inside this place, okay, how much air, let's say if this air cross, how much air inside this surface here, okay, sorry, I said instead of calculate the air cross, cross this, go over this surface, they calculate how much inside here, okay, how much air inside here, okay. That's why it's called divergent, means you're away from the source. So when I go inside the source, okay, and then how much you get inside here. So they said, well, whatever you get inside here, that's whatever you go outside. So that's basically what they means. And so that's for using the divergence theorem. So using divergence theorem, use this part, okay, but they're able to connect this part with these things here. Now we can learn how to verify this. So we said it. So this is eventually it just equal to Q divf. Okay, because calculate this is tough, but calculate this is very easy. Okay, so now they want to verify first. Verify means so that these two sides indeed equal. Means that this indeed equal. So we're going to do a first problem. Okay, this is the number 6. It said verify. Now for sure you're going to have to verify because this is very, very important. So verify Green theorem, verify divergence theorems, and verify Stokes theorem. You all need to know how to do that. So verify that line integral, okay, is the same as finding the integrate the volume with the divergence. Okay, they said to calculate line integral, mean to calculate the flux across the surface is same as to calculate the volume of the integral. Okay, this is a volume of the integral times by the divergence. Divergence means away from the source, so going into another place. So how much going over is same as how much going inside. That makes sense, isn't it? Because you want to calculate how much go over. If I can calculate how much inside the thing and times by the divergence means the in and out, the let in and out times by the volume, so tells you how much it actually go over the surface. So now, of course, when you listen to this, you will say, that doesn't make sense to me. But what's most important is the calculation. Would the calculation make sense to you? Okay, would they really tell you that it's true? So we're going to verify this. So yeah, to calculate this one, same as calculate that. Okay, calculate this is same as calculate this. So that's in number 6, and we are given this is surface. This is surface. It doesn't look too good. So it's a okay, it's like a block, and then they tell you this is X, Y, and then Z, and then I'm going to they said find the verify divergence theorem for this surface. You are given the vector field functions equal to X, Y, Z, and then X plus Y. That's the vector field, okay? And then they said that, I think that's all they gave us, okay? Then they said that calculate the calculate the flux for this volume and verify it. means verify by using using surface integral to calculate first. It will be same as using the divergence theorems. So my hint to you is always calculate this one first. Why? Because this one is a lot easier to do. Then it kind of gives you the answer, okay, for it. Because both sides' answers should be the same. So you calculate this one first, okay, and then to see what the answer possible is equal to. Oh, they give us they give us a 4 here, okay, 4, 4, and then 4. Yes. So they said the surface on the top, okay, the surface on the top here. So they use S5, so on the top here. Oh, okay, S5. I don't mean to cover the 4. S5 equal to S5 is G equal to 4 minus X. Okay, and then this is S1. The sign here is S2. S2. Okay, on the other side is S4, and the back is the back here. Okay, the back is S3. So S1, the size S2, S3 in the back, S4 on this side, and the S5 is on the top part. The top part is G equal 4 minus X. So I'm going to calculate S1 first. Oh, you know what? Sorry, I said calculate this one first. So I'm going to go the right hand side first. Okay, the right hand side, find the divergence first. Divergence F equal del M over del X. This formula is given on 15.1. Plus, now divergence is a left flow rate. Okay, left flow rate. That means it's a scalar. So del N over del Y plus a del P over del G. It's a P here. So M to X, so then we have Y left. N to Y, you have no, so it's a 0. P to G, you have a no, so it's a 0, so just equal Y. So that's kind of nice, but it's not a variable, but it's not a constant. For constants, it's better. It's a variable. So to calculate this one, is equal to, now you're looking for this volume here, okay? So I'm going to go X from 0 to 4. So I'm going to put F. Now you can put anything you want on, who go first, doesn't matter. What matters is make sure the outside one is a number, okay? And so you can see here, okay, X is a 0 to 4. This is a square, okay? It's a square, then your Y should be 0 to 4 also. Y is 0 to 4, so dy. And then the top is a from the bottom to the touch the surface, okay? Bottom touch the surface. And then so therefore it's a 0 to G 4 minus X. And then divergence is Y. So I forgot. I need more room here. So dg dy dx. So that is very easy to calculate, isn't it? So 0 to 4, 0 to 4, and yg 0 to 4 minus x dy dx. That's equal to 0 to 4. 0 to 4, y, and your g is equal to 4 minus x, dy, dx. And I have to erase this part here. Don't have enough room. Okay, so that becomes 0 to 4, okay. This is x here, this is y, so y comes out 1/2 y squared. So 4 minus x, this kind of like a coefficient, 1/2 y squared, and then 0 to 4 dx. And then you put it inside. So to save the time in here, so I can tell you this just equals 16/4. Okay, so I don't like to spend too much time on doing the basic integration. And then next thing is, so you know your answer is 16/4, so you put it on the side. You say, okay, my answer should be, this should equal to 16/4. So 16/4. Now, I need to do the surface integral. I need to verify the other side. Other side would be, you need to start S1, S2, S3, S4 like that. So you can see how fast I use the divergence theorem. But if you're using the material from 15.6, okay, then you're not that lucky. Then you have to, if I ask you to verify something, I wouldn't give you that hard to verify or that long, okay? So now we're going to go the left-hand side. The left-hand side, I'm going to start S1 first. For S1, your bottom is g is equal to 0. Okay? And then your n here, okay, your n is equal to 0, 0, -1. That right? Because that's when you're pointing to the negative side of g, so you're 0, 0, -1. So your n is equal to 0, 0, -1. And then you take f dot n, your f dot n will equal this dot 0, 0, so equal to x plus y. And now you're going to integrate, okay, for this one, for S1, your surface, your area is x and y, okay, so x and y, so it's 4 and 4 here, so 0 to 4, 0 to 4, x plus y, dy, dx. And again, the very basic integration, so I'm going to tell you what I get. Is equal to, guess what happened? Equal to negative 16/4. Okay, that's what I get. It means that what's negative means you are flowing, it means more inflow than the outflow. Okay, so more inflow than the outflow. Then that's my first one, S1. Now I'm going to go S2. For S2, that would be right here. That is this plane is a y equal to 4, right? This is a y equal to 4. So that's a y equal to 4. And for y equal to 4, let's see what's my n, okay? Your n is going to be like this, right? So your n is equal to x is equal to 0, y is equal to 1, because you're pointing to a positive y direction, so 0, 1, 0. So your n is equal to 0, 1, 0. And then your f dot n is equal to just a g. Okay? And then now we're going to look at this one. So you're looking at the gx plane. Okay, this is x, this is g, and you're coming down. Did you see here? You're coming down, right? So that's the same equation. This one, right? Same equation that. So this is 4 and 4. So this is x plus y, x plus z equal to 0. Z equal to 4, I'm sorry. S plus y equal to 4. S plus z, see, I keep saying that wrong. Okay, so you can see s equals 0, z equals 4, z equals 0, s equals 4. And that means your g, okay, your g is equal to 4 minus x. Now you're going to do your surface integral. Your s from 0 to 4, your g is from 0 to 4 minus x. And then your function f dot n is equal to g, and then dg dx. Again, to integrate this is very basic integration, so I'm not going to do it, and I will tell you also my answer for this one is equal to 13/2/3. positive means more outflow than the inflow here, okay? So when the heat goes inside, let's say air go inside, more inflow than outflow for this one, for this surface, but there's a more outflow than inflow for this surface, okay? So that's for S2. Now I'm going to go to S3. So I'm going to erase that. Don't have enough room. S3. So S3 is right in the back. So in the back, okay, so my N right here, okay, my N will equal to, well, -1, right, pointing to the -1 direction. So -1, and the rest of it 0, 0, okay, and so then the plane, the function, the equation to present this plane is just x equals 0 because you have this origin, right? This is a positive x. Right here is x equals 0. And my n is equal to -1, 0, 0. Okay. And then now my f dot n will be equal to -xy. Okay. And because again this is a YZ plane this time, it's a YZ. Okay, this is a YZ plane. You know, earlier the answer is -16.4. Okay, so make sure you write that down. So at the end you have to add them all together. So this is a YZ. Okay, so YZ plane. So that means you're going to go still 0 to 4, 0 to, but these parts are different now. Okay, hey, I don't need to calculate this one. -xy, because x equals 0, so that just equal to 0 now. Okay, f dot n is -xy because x equals 0, so it just comes out equal to 0. And because I put the x equals 0 inside here, the other thing I don't have that. Okay, I don't have that, so that's why this is y equals 4. So I'm not able to cancel this, reduce this one, so I don't have that luck. So my S3 is just a 0. What's the U 0 means? It means that inflow and outflow is the same, okay? So therefore, the divergence equals 0 on that part. And then now we're going to go to S4. For S4, we have this side, okay? This side. So that will be the planes of y equals 0. And for y equals 0, my n, okay, my n is equal to 0, -1, 0. Sorry, I had to write a little tiny bit. So my n is equal to 0, -1, 0. Okay, and then my f dot n, f dot n here, so it's just equal to -8. What happened here? I get the same thing as S2, but S2 minus positive z, is that right? So this is same as S2. Okay, S2 is a positive z. If you look at the note, SZ is a positive 2, and S4 is a negative. What did I say? I said S2 is a positive z. Okay. So this one, the f dot n is equal to z. But for S4, it's a negative z. So that means their flux will be exactly opposite. This one, the flux equals 13.2. So this will be -13.2. So I don't need to calculate it, okay? I think 13.2 over 3. Because this one is 13.2 over 3. This will be opposite of that. And then now my last one is S4. So S4. So my goal is to get 16.4 at the end. That's the answer I have from before. Well, S5 is a surface on the top coming down, okay? It's like a slice. So now this one you have, it's not a straight, it's not like this one. This one's a parallel to the parallel to the xy, parallel to the axis, okay? Parallel to the YZ axis. Now those are easy for you to get this, okay? That is just like your gradient also, because they're perpendicular already. So but S5 is not that lucky. You get Z is equal to 4 minus X. Then you need to calculate the gradient first, okay? So we're going to get the G equal to Z minus 4 plus X. And then we go del G. Do not parameterize a surface unless you have to. Unless this one doesn't work, okay? And then del G equal to GX, so it's 1. Gy is 0, Gg is equal 1. So equal 1, 0, 1. And then F dots del G, okay, is just equal to xy. This dot is xy. This dot is 0. This dot is equal to x plus y. And now I'm going to integrate, okay, like this on the top. So on the top, it slides down like this, okay? So it comes out like this. When you project, now this plane here, you basically project like on the top. When you project from the top, look at it, you just get this, is that right? Because remember the surface, when you change the area, you basically project the surface onto the kind of like onto the place you project to. So when I project this plane here, okay, maybe I can show like that, okay. When I project it down, what I just seen a rectangle there, right, or a square, right? You project down, you just seen that. So therefore, when you project this surface onto the xy plane, okay, you are just seeing a square. So that's your R here, okay, so there are 4 and 4. So then when you calculate dA and then R, you are just equal to from 0 to 4, 0 to 4, xy plus x plus y dy dx. So that is pretty straightforward to integrate, okay? So these just a base, you guys already know how to integrate this very easily. It comes like 128. Okay, just respect the y first. Some still make mistakes, so make sure be careful, okay? Sometimes the easiest thing to do, you could easily make a mistake. So this is 1/2 y squared comes out xy, the 1/2 y squared. So this, just show you that's one step, okay? Y comes out as a 1/2 xy squared plus xy plus 1/2 y squared. And then you put 0 and 4. And then you calculate then respect to x. You get 128. Now you get all S1, S2, S3, S4, S5. Finally, you can add them together. Your goal is to get 16.4, okay? So now the total first, from the line integral, okay? From left-hand side is equal to, first for S1, S2, S3. So S1 is equal to negative 16.4. S2 is equal to 13/2/3. S3 is equal to 0 because the nothing, it means the in and out is the same. And then S4 is equal to negative 13/2/3. Okay, this one. So negative, it means that you have more in than out. And then the last one is 128. And this cancel. 128 subtract 16.4 is equal to 16.4 also. So it match what we have here. Okay, so it means that both sides equal. So you can see that you just need to believe, okay? You say, oh, it's really, it means that go over this surface, okay, go outside. It's same as what's inside. Well, it is, okay. I mean, it's not just what's inside, it's what's inside multiply the divergence, okay. That means that divergence means that at one point, and every little hole here, there's an in and out, okay. So it's more in and more out in each divergence. Each one's a difference. So that is how you verify, okay. So you can see how the beautiful for divergence theorem is a lot faster, right? We did that right hand side a lot faster than the left hand side. And then we have so I'm going to stop here, then I'm going to continue from part 2 because this is getting long, okay. So I stop here first, and then we're going to do part 2.